A divergence looks at how much there's rotation, if you will, from a particular point. You call it the source point. To measure that, Gauss said was equivalent to computing the volume of that fluid as it also crosses that particular surface. What Stokes comes up with, and the history of Stokes and um, Michael Faraday is very interesting in the group that they had in England. But what he does is he says that it is possible to equate the so-called flux, or the line integral, by evaluating the curl. Let's see. He's If it's the line integral, then we're concerned about the orientation along the base region here. And so he says, by all means, you want the orientation to match up with how the particle is moving along the boundary, moving in a counterclockwise manner. His criteria is based on Green's theorem. So when he talks about this region and the curve, he uses the same criteria for Green's theorem. Then what he does is, then he jumps and he says, if you want to compute the line integral, we can focus on the region down here. Or he said, if you want to compute the double integral, he said you can do that as well by looking at the curl, but now this is the curl on the surface. So he wants to equate both. I can evaluate Green's theorem, what happens in the xy plane, or he says, look, that's equivalent to evaluating how much curl is happening from the rotation around this particular source point, where that n normal vector is pointing out of. So he said, look, I can investigate what happens along the surface with the rotation of the fluid, or you can only focus on what's happening down here in the region. He said, either way, it doesn't matter. You get the same thing. Well, somewhat controversial back then, but today we just take it to be so. It's interesting how things that could be controversial for some people, and then through time, it doesn't become that big of an issue anymore. Yeah. You know, in the church history, issues like what day you worship on or how you baptize, you know, there were some people who were excommunicated because of how they, took beliefs on those matters. Some even killed. But nowadays, okay, you just go to that church over there. It's not okay, they do that over there, We don't do that. You go over there, and it's okay. Nobody's going to be excommunicated. Nobody's going to be burned at the stake, But issues a long time ago that affected people, nowadays, it's not that big of an issue. And my question philosophically is, the issues that we're dying over right now, if the Lord delays his coming 50, 100 years from now, would it really matter? I tell you what, just you don't have to go too far. Just take America and look at Democrat, Republican. I mean, this is some cutthroat type stuff that's going on right now, But you think 100 years from now, would that really matter to people, 100 years from now? Yeah. I mean, you think about, some of the issues that were faced by people 100 years ago. I mean, some of those issues, those big issues, okay. People are getting over that. So, anyway, a lot of what was going on in the math world, you got to think, guys, 100, 150 years ago, mathematics, that was Xbox Live. You know, man. I mean, that was it. This is like Fortnite, you know, man. I mean, this is YouTube, man. Oh yeah, that's right. That's right. Very controversial. You know, what's the center of the universe? Is it the earth? Is it the sun? Is the earth flat? You know, man, some folk. That's that's right. That's right. You know, nowadays, let's just go to Subway and eat a sub sandwich. You know, we'll talk about it over lunch. You know, over a sub sandwich. But you know, back then, 200-300 years ago, those issues for the church, man. Hey, sheesh. Even you know, you going back 500 years, 1,000 years, to the days of the Council of Nicaea. The Council of Trent, when they were discussing the Trinity and, you know, is God three in one? That time, I mean, these people, they were being butchered, man, if you thought otherwise against, you know, what they considered the norm to be. So nowadays, again, okay, that church over there, they believe in that. You go over to that church. You know, you believe in oneness, you go over there. You believe in the Trinity, you come over, you know, so that type thing. So, yeah, well, let's see. So here, he's concerned about the orientation of the movement around the curve. Again, this is the criteria based on Green's theorem. So the conditions there from Green's theorem. And so here's what the theorem says. He says that I can find the line integral based on what's happening in the surface with respect to the region. Here's what he does, and I will do the same thing. He takes this so-called curve and he points to the region, and I'm going to also take what happens on the surface, and I'm going to try to point that toward the region as well. And I'll show you my get around Stokes theorem in just a minute. So he says, look, I can compute what's happening with respect to the line integral, and he says that's tantamount to the movement of the fluid with respect to its curl over a double integral of the so-called surface. Now, here's what I use. You remember that n, if it's shooting outward or upward orientation, this guy is the gradient of g divided by the norm of the gradient of g. And ds is given as this so-called surface area that we get the surface integral from, that this guy came out to be the gradient, the norm of the gradient of g times dA. dA is the base area. So this guy can point us to the region, to the XY region. So if that be the case, then we have here, according to Stokes, this line integral, he says, can be computed by the double integral over the surface of the curl of f dot product with n ds. And here's what I came up with, and this is what I use, that this is equal to the double integral over the region of the curl of f dot with the gradient of G dA. Oh, look, because n ds is equal to, now that n is the gradient of G divided by the norm of the gradient of G, and then ds is the gradient, the norm of the gradient of G, that is, times dA. So those norms cancel out, and all we have is just the gradient of G dA. Okay. So that's what I use. Now with that, so I only focus on this guy, and I think it makes it a little bit easier when we're simplifying for the so-called Stokes theorem. Let's see. Again, he's considering how much rotation is there about some fixed point. So to measure that rotation, he has this, what we consider the curl, right? If there is no curl, then what does that say about the system? If there is no curl, if the curl is zero. Right, you get back. And so you can kind of imagine, go back and study it, you can kind of see how Stokes was so connected with Faraday, with his theory of the controversy, the law of conservation of energy, and see how they go together. Right. That's right. He did a whole lot. He sure did. Yes. Yeah. Yeah, he was in in Great Britain. That's right. Yep. Yes, sir. Yeah. Mm-hmm. They had a group called the Cambridge Group, and mathematicians and physicists would meet, and they would challenge each other with probing questions that were difficult to solve, which basically what we study in physics and mathematics, calculus 3 and vector analysis today is basically, what they somewhat some they deduced, but a lot of it they compiled and connected. They connected a lot of Einstein's information, not Einstein, Newton, I'm sorry, Newton and Leibniz's information to what we know today as the calculus. Well, you can also think Carl Friedrich Gauss for a lot of the calculus in terms of proven by the rigor that we use in terms of epsilon and delta. So let's see. Let's first, we look at the curl. So two things we do. Find the curl of F. Number two, compute the gradient of G. I better add a third one here. Find, should say determine the region. Determine is better. Determine the region R. Okay. So first we find the curl. Remember, it has that formula. It's the determinant of a 3×3. The first row is I, J, and K. The second row is the operator of the partial derivatives. Then the third row would be the components for F, X, Y, Z. Y, and then Z. So to find the first term, let's put this information there, j, then plus k. Here we are expanding along the first row. So we delete the ith row and ith column, so we have the crossing of the partial of z with respect to y, that's 0, then minus the partial of y with respect to z, that's 0. Then we go to the jth term, delete its row and column, so it's the partial of z with respect to x, that's 0, minus the partial of xyz with respect to z, that's xy. Then for the kth term, delete its row and column. We have the partial of y with respect to x, that's 0, minus the partial of xyz with respect to y, that's xz. So we can clean that up. So the curl of f is equal to xyj minus xzk. So number 2, we look for the gradient of g. Well, here we take the surface. It's given as s here is 6x plus 6y plus z equal to 12. Just write that here. 6x plus 6y plus z equal to 12. I think I wrote that right. Yes. So we said that g is equal to little z minus little g of xy. Basically, you get everything on the side of little z. Well, I mean, that's happening except at 12. So just to be accurate, this is 6x plus 6y plus z minus 12. And we take its gradient, get 6i plus 6j plus k. Need to find number 3, the region. So if we're given 6x plus 6y plus z equal to 12, it's in the first octant. Had to go pick that up. So let's see. Do you notice here that z is equal to 12 minus 6x minus 6y? Right? And if we let z equal to 0, why let z equal to 0? Because based on my criteria, I want to reduce, what page is this? I want to reduce this double integral to the region R. R is in x and y. Okay. So this implies then that x plus y is equal to 2. I let z equal to 0 and then just divide through by that 6, you get x plus y equal to 2. And so from there, can you see that y goes from 0 to 2 minus x? And x goes from 0 to 2? So now we get it. So now we can compute this double integral. We have that curl of f. It's going to be dot product with the gradient of G, and then this is dA. This is over the region. So now I can put the region in there. This region goes from 0 to 2 minus x. X goes from 0 to 2. The curl we found to be x, y, j minus x, z, k. And this dot product with that gradient of g, that's 6I plus 6j plus k, and this looks like this is dy dx. Let's get a little bit rowdy. R-O-W dy. Yeah, okay. Yeah. My high school days. So there's no I component on the for that curl, so this just becomes 6xy minus 6xy minus xz. And this is dy dx. So now we integrate with respect to y. 0 to 2. This is 6xy squared divided by 2. Just write that as 3x y squared, then minus xz y, and y is evaluated from 0 to 2 minus x dx. We have the integral from 0 to 2. This is 3x times 2 minus x to be squared. Oh, that z, oh, didn't see that. Z is equal to 12 minus 6x minus 6y. I need to go back. Sorry, Charlie. I'm reducing it to r, so I have to get rid of that z, right? So I have to replace the z with what it's equivalent to. This is 6xy minus x times z is 12 minus 6x minus 6y dy dx. Oh, now we're going to simplify some more. 0 to 2, 0 to 2 minus x, 6xy minus 12x plus 6x squared plus 6xy dy dx. Simplify that one more time. So this is 12xy minus 12x plus 6x squared. Dy dx. So now integrate with respect to y. So this is 6xy squared minus 12xy plus 6x squared y. And the y is evaluated from 0 to 2 minus x dx. So wherever I have y, I'm going to put 2 minus x. So this is the integral from 0 to 2. 6x times 2 minus x to be squared minus 12 times 2 minus x plus 6x squared times 2 minus x. Evaluate at 0, they all go out to be 0 dx. Now let's simplify all of that. This is 6x times 4 minus 4x plus x squared minus 24x plus 12x squared plus 12x squared. 6x to the third. Simplify one more time. Integral from 0 to 2. This is 24x minus 24x squared plus 6x to the third minus 24x plus 24x squared minus 6x to the third. See, the 6x to the thirds cancel. 24x squared minus 24x squared cancel. 24x minus 24x cancel. 0. Boy, isn't that something? All right. Subway sounds about right about now, you know. Subway has the coolest breakfast sandwiches, folks, let me tell you. I get the egg white and the turkey and then the flat bread. Oh, man, with all the veggies. Just to put everything on there, right? Yeah, good stuff. Okay, I'm going to do this one, then I have one more for you to do, and I'll let you do the last one. So it's just 3 problems here. I do 2, you do 1. So here, compute the line integral by computing the double integral given by Stokes' theorem. In the homework, it says compute both sides, compute the line integral, and then also compute the double integral. Look, just compute the double integral. The answer you get is going to be the same answer for that line single integral anyway, so just put the answer over there. On the test, you just compute it the way I'm doing here. Just compute this using the double integral based on the curl. Yep. Yep. So you know my method. Whatever I do, that's what I also expect of you as well. So the first thing we do is compute the curl. Z squared 2x, then y squared. Delete the ith row and column, so we have the partial of y squared with respect to y, that's 2y, minus the partial of 2x with respect to z, that's 0. Now delete the jth row and column, it's the partial of y squared with respect to x, that's 0, minus the partial of z squared with respect to z, that's 2z, excuse me. Now delete the kth row and column. It's the partial of 2x with respect to x, that's 2, minus the partial of z squared with respect to y, that's 0. Okay, so this curl of f is 2yi plus 2zj plus 2k. And then this is 2yi plus 2 times z. Let's go ahead and convert that z to its xy values. 1 minus x squared minus y squared j plus 2k. Now secondly, we need to find the gradient. So capital G is equal to z plus x squared plus y squared minus 1. This implies that the gradient of G is 2xi plus 2yj plus k. Now that region here, if you let let z equal to 0, this implies that you have x squared plus y squared is equal to 1. So it's a complete circle. Theta goes from 0 to 2 pi, and then r goes from 0 to 1. So the region here is 0 less than equal to r less than equal to 1, 0 less than equal to theta less than equal to 2 pi. So now we put everything together. So you have this double integral. The curl we got to be 2yi plus 2 times 1 minus x squared minus y squared j plus 2k. This dot product with 2xi plus 2yj plus k. And then here, I'm just going to say dA. This is over the region. Double integral. You see the dot product, I get 4xy plus 4y times, parentheses, 1 minus x squared minus y squared, and then plus 2. Again, dA over the region. So now we simplify that. I think I can get it here. This is 4xy plus 4y minus. Tell you what, I don't want to go into all that because I'm seeing something since I'm converting to polar coordinates. Let's do that now. So this is 4. The x is r cosine. The y is r sine. So I have r is r squared, but since we're converting to the polar, it's going to be times the r. So r cubed cosine theta sine theta. Need to put it down. It's the same thing. Don't erase. I'm just going to put it down here. Need more space. So 4r to the third cosine theta sine theta plus 4r times another r squared sine theta minus 1 minus r squared. And this is plus r. I'm going to evaluate first with respect to theta, since it's going from 0 to 2 pi, and then dr. So 0 to 2 pi, 0 to 1. I think theta, r is going from 0 to 1, yes. All right. Simplify this, 0 to 1, 0 to 2 pi. This is 4r to the third cosine theta sine theta plus 4r squared sine theta minus 4r to the fourth sine theta plus 2r d theta dr. So now we evaluate with respect to that theta. So this is the integral from 0 to 1. This is 4r to the third. Let u equal to sine. Du is cosine. That becomes u squared divided by 2. So we get sine squared theta over 2. Integrate with respect to theta. So the integral of sine is negative. Erase this and put a negative sign there. So this is negative 4r squared cosine theta plus 4r to the fourth cosine theta plus 2r theta. theta is evaluated from 0 to 2 pi dr. Now, when I plug in for sine to be 2 pi and 0, I get 0 for that guy, right? Here, cosine theta becomes a complete loop. 1 minus 1 when I evaluate cosine at 2 pi is 1, then minus cosine 0, that's 1, so that's 0. This is 0. So all we have is just the integral from 0 to 1. Evaluate this theta on the end at 2 pi, so that's just 2r times 2 pi dr. So you get 4 pi times the integral from 0 to 1 of r dr. This is 4 pi r squared over 2. Evaluate the r from 0 to 1. Just get 2 pi. Okay. Now just one more, and I want you to do this one, and that will conclude the day. Oh yeah, this one is good. It works out, and I love how it works out. So I think you'll enjoy this one. It's like I'm talking about a song. You know? I think you'll enjoy this song. Yes, sir. Yes, sir. What'd you get for the curl? 2zj. Very good. What about the gradient of g? I get, so it's x over the square root of 4 minus x squared minus y squared I plus y, because you know g is equal to z minus the square root, right? So those negatives will cancel. Plus k. And then the region, if you let z equal to 0, you get r is bounded from 0 to 2. And then theta goes from 0 to 2 pi. Oh, it's a good question. Remember, his question is, can you do that with z? And I say you can because I'm investigating this. This is the gradient of g dA. You're only concerned with the reduction. I'm only concerned with what's happening in the region with respect to x and y. For us, polar coordinates are in theta. Yes, sir. If you wanted to investigate the true curl nature, focusing on the surface, then I'm dealing with x, y, and z. But he says that's equivalent to the line integral along the curve, the base curve that's happening in the region of x and y. Yes, sir. And he cares about both, but he says that both are equivalent. Either I focus on what's happening in the xy plane, or you can also focus on what's happening along the surface itself. Either you focus on the surface or around the curve, the orientation, based on Green's theorem. He said both are equivalent. So that's why I take both of them. And this, I've been working on this. I need to publish this because this is my theory. Call it Stokes / Williams. Now, anyway, it works. It works. So you have this double integral. I'm focusing here from 0 to 2 pi, and then from 0 to 2. When you do that curl dot with this gradient, all you're concerned with are the jth terms, right? So that's 2z times y, and if I could write that, this 2z times y over the square root of 4 minus x squared minus y squared. Well, the z is the square root, right? So they cancel out. So all you have left is just 2y, or, and forgive me for the different coordinates, should convert it all to either rectangular or symmetrical. So let's do the conversion now. This is 2 there. This is 0 to 2 pi, 0 to 2. And this becomes r squared sine theta d theta dr. Once you get 0, when you do the evaluation of that sign, you get cosine. Going from 0 to 2 pi, we get 0.